Okay, this is the part 2 presentation on optical force and optical sorting. Once again, we're grateful for NIST contract funding. This method is based in Mosaic. What you do is you set up bucketized velocities. So here's a particle over 5 frames, and you put its velocity in bucket 1 to 2, and you put its velocity from 2 to 3 in a different bucket. And you do this for all the particles. And looking at the movies, this is the original movie, and you can see some cavity swings in power. And you convert that to binary by looking at the histogram of the image and setting a threshold based on the histogram. You do that for each frame. In Mosaic, you can specify displacement and link range, and it outputs particle position versus frame number, and you export that to Excel, and a Python script was written to read this data in and bucketize it. Now the Mosaic tracks particles by, and you can see the individual drawing of circles on the particles. So it tracks it over time. And if you plot the number of frames tracked versus number of particles tracked, first they were over 200,000 particles tracked. In the non-laminar case, all the slopes are similar and highly linear. In the laminar case, there's this difference between slopes. This is the one pass, half pass, and static cavity, and here's the contracting and expanding cavity. So it may make analysis a bit trickier. If you look at the number of frames tracked, you can convert that to time, and this is normalized speed, or meters per second. We see a difference between contracting and expanding cavities, these are this line here, versus static and one pass. That indicates a deceleration force was applied. This is the non-laminar case. If you apply initial offset to put all of them at the same level at this frames track number 2 to 3, you can then readily compare and assume that number of frames tracked is time. And you measure acceleration by comparing the velocity change over time. And so that's what we did here. In this table, this shows non-laminar. There was a optical force calculated to be around 87 piconewtons for contracting cavity and 25 for expanding. It was a bit higher for laminar at 80 and 230. The static was negligible in non-laminar and slightly there in laminar. Looking at Mosaic PDF, this shows the one pass and static PDF. So velocity is on this axis and counts and bin are on this axis. And you can see that these are faster than the expanding and contracting cavities. That indicates deceleration force has been applied. Now we also looked at phase Doppler, which is Dantec instrument, to look at, this is PDF of droplet size, and this shows you velocity versus droplet size. There's basically no correlation between droplet size and velocity, so it's not really useful to look at that. The other method is pathing. So what you do is you take a time standard deviation for a group of frames, get a streak of light, and find where that light is, and then curve fit it, either linearly or with a polynomial fit. That gives you an idea of curvature. And we see for expanding and contracting cavities, they were higher than 1 pass, which is no force applied. And static was slightly a force. In this method, we're looking to do what Mosaic does just for frames 2 and 3, or the first frames tracked. This makes the analysis much faster. So basically what you do is you find particles that have no near neighbors, then look at the next frame, and you know that that particular particle has been tracked. So it's only valid for those 2 frames. You append that data, velocity data, to an image by location, and then you can time average it and find the cross section. So this chart shows you vertical and horizontal axis. So this is actually calibrated, so it's distance in the cavity. And this axis shows you velocity. And so again, we see 1 pass and static cavities are higher velocity than contracting and expanding cavities, indicating that a deceleration of force was applied. You may have noticed a pattern by now that contracting cavity was a bit more force than expanding. I'll talk about more about that in a later slide. This is the non-laminar case, similar to the laminar cases, a bit noisier, but similar. To conclude, it seems there's confirmatory evidence indicated for en masse optical force. A point source laminar flow is not required. Optical force measurements seem to agree with tweezing, 10 to hundreds of piconewtons. Optical force level can be configured by cavity mirror velocity or by power, laser power. And we could probably go to smaller particles by increasing laser power, because the cavity light scatters broadly. The particle velocity can be fast, and these are currently low irradiances. The laser was a 1-watt laser. It seems that the interference pattern activity is indicated as a main driver in optical force, not contracting cavity. It's kind of preliminary evidence because we varied cavity velocity, and if aliasing duty cycle was at 100%, the force seemed to be maximum. So optical sorting was not observed by size. A standing wave period of 532 nanometers was too small for the microscope objective, and the static cavity's interference pattern drifted randomly and slowly. So if you try to close the loop, meaning you maintain cavity path length, it may be tricky because the line width is small. You can make the laser line width bigger, but I'm not sure what would happen there. An open loop, it was drifting slowly, so that may be the reason why some force was applied. For our test setup, the aerosol was extended and mixed, so likely a shift in randomly arranged particles at line A still leads to random arrangement at line B. So a procedure to measure droplet size is proposed as follows. What we would do is collect voltage data and camera data simultaneously. You average the voltage, measure particle acceleration with the camera. You vary the stage velocity or laser power and repeat these multiple times. And you measure particle size independently with another instrument perhaps. And then you have a correlation of force and voltage versus acceleration obtained with the camera. And so now you can measure an unknown aerosol droplet size. Here's some references. Here's our contact information. website, email address, and toll-free phone number. Thanks for your attention. Have a good day.